Hi, my name is Gaël Letarte and I am a PhD student at Laval University. In this short video I will present our work that was published at NeurIPS 2019 on Dichotomize and Generalize PAC-Bayesian binary activated deep neural networks. This is joint work with Pascal Germain and François Laviolette from Laval University and Benjamin Gage from INRIA Lille and UCL. In this work we analyze deep neural network with binary activation using the PAC-Bayesian theory. We developed a framework to train such networks and we obtained non-vacuous generalization bounds for our approach. But first, let's introduce the relevant notations. We stand in the supervised learning setting where a learning example consists of a description label pair x and y. All examples collected for a task constitute the training set S, and we assume that they are sample IID from an unknown data generating distribution D. Using a learning algorithm, we search amongst the family of predictors for a predictor f, which is a function mapping the input space to the label space. We assess the quality of a predictor's prediction using loss function. Our objective is to find a predictor that minimizes the generalization loss, which is the expected loss of a predictor according to the data generating distribution T. However, this distribution is unknown. Thus, the challenge is to achieve our objective while only having access to the empirical loss, which is the mean of the loss on the training set. A powerful tool to obtain insights on the generalization performance of predictors is statistical learning theory, such as the PAC-Bayesian theory. PAC-Bayes provide PAC generalization guarantees on Bayesian-like predictors. The probably approximately correct learning framework gives probabilistic upper bounds on the generalization loss. The probably part refers to a confidence parameter delta that the bound is accurate over the sampling of the training set from the distribution. The approximately correct part involves a real valued function epsilon that encodes the upper bound based on the empirical loss, the number of examples, the confidence parameter, and other quantities usually related to the complexity of the predictor family. The Bayesian part of PAC-Bayes is that we are working with distributions over the function space. From a prior distribution P that encodes prior knowledge related to the task, we seek to learn a posterior distribution Q that yields good performance. The distribution over the family of predictor can be interpreted as a majority vote or a randomized predictor, but in our case we consider it as a predictor aggregation. To give an idea, we present a PAC-Bayesian theorem as we used in our work. It follows the PAC guarantee recipe with the addition of the expectation according to the posterior distribution Q for the generalization and empirical losses. Also, the epsilon function is explicitly defined here, and we see that it depends mainly on the empirical loss, the number of examples, the KL divergence between the prior and posterior, which controls the complexity of the model, and an hyperparameter C that we can tune. Now that PAC-Bayes is introduced, let's see on what kind of predictors we are going to apply it. We are working in the binary classification setting where the label is either -1 or 1. The predictors are binary activated neural network with a classical fully connected architectures of L layers of Hidden-side DK, and each neuron is activated by a sign function. The difference with binary neural network is that we have real values weight matrices, while binary neural network have binary weights to optimize memory and computation. We have the following prediction function f, parameterized by theta, with a single binary activated output neuron. Let's start our PAC-Bayesian analysis of such predictors with a simple case of a linear classifier. The origins comes from the work of Germain et al. Applying PAC-Bayes to linear classifiers defined as binary predictor parameterized by W. The strategy is that, over the space of all linear classifiers, we consider a Gaussian prior and posterior. Then, they found that we can express the aggregation of the binary predictor according to the posterior distribution in terms of the Gauss error function ERF. This is a key concept. By putting a Gaussian distribution on this binary predictor and taking the expectation, it gives us an expression in terms of the ERF function, which is easy to compute. As you can see on this figure, the ERF function behaves a lot like the tanh function, which is used in deep learning as an activation function. Using the linear loss, they were able to minimize the PAC-Bayes upper bound on the generalization loss by gradient descent on W. Also, the KL between our two isotropic Gaussian distributions is simply the norm of the difference between the posterior and prior. In our paper, we tried to apply the same ideas presented in this slide, but for networks with hidden layers where the earth function acts as an activation function. So let's look at a single hidden layer network defined by the binary predictor f parameterized by theta. Again, we consider an isotropic Gaussian posterior distribution centered in theta over the family of all networks. Then, we seek the Q aggregated predictor by taking the expectation. First, we can see that the upper part of the network is like a linear predictor over the hidden layer's activation values vector that we call S. As they are sign activation, we have a finite numbers of possible activation combination or S values. Thus, we can discretize the integral on the lower weights as a sum over the 2 to the power of d1 possible values of S. With that, we obtain an exact closed form of the aggregated predictor, which is a sum over all possible activation on the hidden layer of two things: the probability to reach this activation S given the input X and the weights W1, and the linear predictor output over this activation S. Unfortunately, we have a sum combinatorial in the number of hidden neurons, which quickly becomes impossible to compute. In our paper, we present a stochastic approximation using Monte Carlo sampling and also how to go deeper with multiple hidden layers. But for now, we are happy to have an exact closed form expression of the aggregated predictor for which we can compute the PAC-Bayesian ingredients. Indeed, using the linear loss, we can easily obtain the empirical loss of the aggregated predictor. And again, the KL divergence is simple to compute thanks to our choice of distributions for the prior and posterior. With all of that, we obtain a PAC-Bayesian generalization guarantee that can be used to drive the learning, help for model selection, and certify the performance of the predictor. Let's look at the visualization of how exactly the aggregated predictor really works. We consider a simple two-dimensional two-moons dataset that we try to solve with a single hidden layer network with 3 neurons. We trained the network for 10 epochs where it reached 100% accuracy on the data. Looking at the aggregated predictor expression, we have a sum over all possible activation S on the hidden layer. In our case, 3 neurons give us 8 possible activation S. For each of those, we will plot their contribution to the sum over the input space, two-dimensional in this case. First, if we look at the right side of the expression, we have for each possible representation S a probability distribution over the input space for the fixed learned weights. We plotted those distributions where a darker gray area means a higher probability to reach this representation at this input data point. As you can see, the input space is divided amongst the representations, but some of them are not used. Next, if we look at the left side of the expression, we have for each representation S a linear predictor output between -1 and 1. Usually, when the network converges without errors, the linear predictor output is either -1 or 1. So basically, it defines if the shaded area should be red or blue. Thus, if we multiply the linear predictor output value to the probability distribution for each of the representation S, we obtain their contribution to the sum, defining the aggregated predictor. As you can see, if we superpose each plot of the representation S, we obtain the plot of our aggregated predictor. Finally, let's quickly look at some experimental results on 6 binary classification datasets. We compare different models from the MLP, which is a baseline network with tanh activation, to 4 variants of our approach, PBGNet, that stands for PAC-Bayesian Binary Gradient Network. Without going into details, from the upper PAC-Bayesian model in blue to the one at the bottom in orange, the more and more the PAC-Bayesian bound is used in the learning process. For each model on each dataset, the colored bar displays the test error, while the black outline bar is for the train error, and the bound value sits on top for PAC-Bayesian models. There are 3 main takeaways from this figure. First, models that don't care about the bound during learning, in red and blue, usually have the smallest training error and test error, but they have no or vacuous bound values. Second, without surprise, the more a model integrates the bound in the learning process, the smaller the resulting bound value is. The best model in orange using pre-training to start with a better prior. Finally, the train test error gap is also smaller generally for those models, which could indicate potential robustness to overfitting. This concludes this short video presentation, and if you need more information, take a look at our paper or the GitHub repo. Thank you very much.